Okay, I could crack on it. Oh, it's okay.
Okay, thank you very much. Thank you very much for inviting me. It's always a pleasure to be here at the center in Natal. And today I'm talking about, this, it's not working here. So the pointer is not working. So today I'm talking about quantum thermodynamics, transport and strongly coupled systems. And this is basically this paper that I wrote with Anton Bruch and Felix von Oppenin from the Freie Universität Berlin. So these are the sponsors. Well, in Brazil nowadays we need a lot of sponsors just to pay our trips because everybody pays, every one of these sponsors pays very little money. It's a little bit, let's say, too basic, but I'm a electronic transport person. And so I'm going back to the early days of classical transport. And just to illustrate that entropy production is a concept which is around in electronic transport since the early days. And basically, if you think about classical transport, the very first papers by Boltzmann, they refer to the route to equilibrium. And basically, Boltzmann came up with this famous H-theorem that he would say that if you start out of equilibrium, then this function H will be always negative. And if you rewrite it in terms of the entropy, it's always positive when you go to equilibrium. And it's only 0 when you reach the equilibrium. So in a transport, in any kind of setting, when you take the system out of equilibrium and you let it relax, then it goes like that. So in condensed matter, so for a long time we were dealing with bulk systems. And so basically a natural evolution of Boltzmann's theorem, or Boltzmann's approach, was this quantum kinetic approach, which permeated most of the works in the 60s, 70s, and 80s before we got to very small devices. And basically, the tool is Green's functions. And you have Green's functions, and basically, if you transform you introduce the Wigner transport in these Green's functions, then you are able to write non-equilibrium Green's functions in terms of 2 times, or a time and an energy. And if you think that things are smooth, etc., so by means of some ansatz of what should be the local entropy density, these concepts were around for a long time, and people were able to understand what would be the entropy production in electronic transport and bulk systems. Nowadays, all this is very well understood, and now we are moving towards smaller and smaller systems, and then we are hitting this, one of the definitions that was discussed in the panel of what is quantum thermodynamics, and basically what happens when you reach the quantum level, the ultimate quantum level in these devices. And so my working tool here is idealization of a quantum dot of a system where electrons are basically confined in this blue region, and by applying some kind of bias or difference in temperature, electrons are injected in this through these red arrows and are collected at the other side. So for everything I'm discussing today, to simplify things, I will assume that the whole dynamics, electronic dynamics within this region is coherent. That means that you have a coherence length which is much, much larger than the typical size of the device. So this is what we do. And basically, all the relaxation processes will take place far away where we actually measure things. Okay, so this is an important thing for this talk. It could be generalized, but this simplifies things. So now I will show you exactly what are the critical thing. And sorry for the colors. So I assume that this internal region is the quantum dot, and it's characterized by some Hamiltonian. In the bath, you have left and right, or alpha and beta. You are coupled to two different baths in different temperatures or chemical potentials, never mind. And there is this coupling term, which corresponds to a region in space which is not by no means small. And depending on how large is the average value of this coupling matrix element, you are in the strong coupling regime. So sometimes it's unavoidable. And in classical physics, you always throw this away. And people have developed also very solid theory for treating this kind of system when this coupling is small. But when it's large, there's lots of ambiguities, and this is the main topic of the talk. So for people that are not familiar with this area, I'm sketching what happens in transport in this kind of systems. And I start with the wide open kind of contacts, illustrated there, strong coupling regime. And if these islands of electrons, they are sort of irregular. And so this kind of measurements, when you measure the conductance, which is 1 over the resistance, in terms of chemical potential of the inside the area, or Fermi energy, if you wish, you see typically curves that go up and down, lots of fluctuations, and this is called in this mesoscopic physics area universal conductance fluctuations. This was a subject of large investigation. Lots of people investigated this theoretically and also experimentally in the 90s, early 2000s. So this is the strong coupling regime. And for the purpose of just counting electrons or current, this is very well understood. What is not understood is heat, current, entropy production. This is the subject of my talk. If I go to the very other side of the slide, I am showing a typical sketch of what happens when you have weak tunneling. And the physics is that you have these islands of electrons weakly coupled to the external world. So one electron wants to enter this island, it has to pay a price. They repel, and so the other electrons don't want this electron inside, and this is what I call charging energy, this U. And typically what you see is these spikes of the conductance, and every time you have a resonant condition, and you have a larger conductance, and the typical spacing between the peaks is U, which is the charging energy. So this is a kind of a funny thing, because many theorists address this problem in the single particle scenario. But for us, in transport and through quantum dots, you cannot really disentangle this. Once you have weak coupling, you have strong interaction effects. So you need another language. And this intermediate regime is the most complicated, because then you have correlations due to some funny effect. It's not the subject of this talk, but this is a strongly correlated system, and you have Kondo effect and things like that, and this is a more complicated thing. And this, from the point of view of electrons, when you have open systems, is the simplest, because you can imagine that you have a charged fluid, the electron comes in and pushes the electrons out, and so the transport is easy. So this is a sketch, and this is basically what happens if you want to do some theory on that. So you have open dots, Coulomb blockade, and Kondo regime, and this is a very many body kind of setting. So our subject today is this. And so to make life simple, I'll just describe you the simplest ever possible model to illustrate the difficulties. And I assume that you have two reservoirs, both at the same temperature, different chemical potentials, in a single level that eventually can go up and down. You can drive it by an external gate potential. So the Hamiltonian is as simple as that. I have still a term like Q, the charging, which makes this a many-body problem, but today we get rid of that. We are just in the simple single particle case, because we are in the strongly coupled regime where many body effects are not that important. And so the key issue is this partition, because this guy is by no means small. And so the first interesting attempt to solve this problem was done by these people here, published at PRL, and it's a very interesting paper. And they kind of found a way around not to treat the coupling by playing some tricks. Let's say they found they used the correct ansatz for the entropy. They used the language of Green's functions, but they had to play a little bit with the spectral function, which stems from Green's function. So it's a complicated game. And this paper actually arrives at some close expressions for the number of particles from which you can derive the current, the energy, and the entropy. There are some ad hoc assumptions. So they get relations which satisfy the laws of thermodynamics. And it, more importantly, it actually describes irreversible driving. So if you drive the system very fast, so there is an entropy production, and the process becomes irreversible. The problem is that this approach does not give the equilibrium forms of thermodynamical functions in the quasi-static limit. So it fails to give you the correct limit of reversible dynamics. So that's not good. And so this was our motivation. It's an interesting paper out, and we try to start from there. So soon enough, so since we are Green's function people, we started to look at the Green's functions of this and try to fix this approach. And so I basically review a previous work where we reduce even further the complexity of the system by treating a single level coupled to a single reservoir. So you don't have a current, but you can shuffle energy and heat from the reservoir to the quantum dot, etc. But you don't have a current going from terminal A to B in this sense. And this problem is very simple because you can have everything under control analytically, and you can write, for instance, the equilibrium relations for standard quantum mechanics, if you wish. And the whole thing is to understand what happens as a function of this drive. And you can expand things considering a small, let's say, a small drive and departures from adiabaticity. So equilibrium is fine. And the nice thing is that you can actually write the first order, which corresponds to the quasi-static reversibility relation. So if you change the sign of the drive, you go back to where you start. And you have controlled expressions for the entropy, for the heat current, and also for the change of total energy. And to improve, you can go to second order and discuss what happens when you have irreversible processes. And this is a very simple derivation. You start from zero order. Here it's a more convoluted, so I don't have enough time to that. If somebody is interested, I can go back and discuss. But this is the key thing here. And the key thing is that the quasi-static reversible first order in drive heat current, you can derive from the thermodynamical relations, and this was what I showed in the previous slide. And then you can also derive from Green's functions, and then you realize that this heat current corresponds to putting half of the coupling into the bath or half of the coupling into the quantum dot. So it's a kind of a democratic ansatz. So you divide the coupling half to the quantum dot, you make an extended system either way, and you can show that the two expressions agree, and then you're happy, so you found a partition which solves your problem. So that's the thing. And so funny enough, in electronic transport, we have shown that all this issue of partition is irrelevant, basically because the electrons cannot stuck in the coupling. But in thermal transport, other people have speculated the symmetric splitting. We're not the first. But if you look close on that, if you put more terminals, more contacts, then there is a lot of ambiguity, and actually the problem doesn't, I mean, if you treat more than one terminal, then the strict doesn't work, and you cannot recover the correct expressions. And there is even a nicer work, more recent, where people started to look into fluctuations, and by playing this trick of putting half and half the partition, you actually arbitrarily fix the fluctuations and introduce a lot of ambiguities in your definition. So it's not a good trick. So inspired by these negative results, we decided to go back to the basics and go to one of the most successful formulas or approaches to describe electronic transport, which is the Landauer-Büttiker. So if you open the books on that, people explain a lot of stuff by using the S matrix, and this was the key contribution of Landauer to our field. So this motto that conductance is transmission, and he was the first guy to point this out, and he was fighting with the community for a decade or so, and eventually he has experiments have shown that he was right. So the idea is that you have, let's say, two terminals in this setting, a quantum dot with lots of levels inside. You have a coherent phase propagation in this dashed region, and you measure outside this dashed region. So all the processes that introduce relaxation, etc., all that happen here where you actually are equilibrated and measure things. So and an experimentalist will have to infer what happens inside by measuring things from the outside. There is no other way. So in this kind of setting. And this is the way that the problem is defined. So people that look at the thermoelectrics have a long history of doing this kind of consideration. And there are the first experiments where people really measure this heat current and basically they infer the entropy production by looking into this in a stationary process. Okay, this is I'm discussing here is just a stationary process. And so the goal is that we have to develop a theory that will reproduce, microscopic theory that will reproduce this and also reproduce or give predictions for a non-static kind of drive. No, drive is not static. So, and this is our idea that we start with Landauer-Büttiker, and then we write the conductance, the transmission. The transmission is given by the S matrix, and now we introduce the possibility that the S matrix depends on time because you have an external drive. So that's it. And so basically the idea is that you have incoming amplitudes where the electrons are, they enter the system equilibrated with a corresponding reservoir, and then they are scattered through the internal region, and they come out in with some other amplitudes. So you have incoming states, which are basically Fermi distributions, and you have outgoing states, which are off diagonal. And then you have all sorts of correlations. And so you can play this game and write the formula for the particle, current, energy, and heat in this formalism. And basically this phi out contains all the information of the out of diagonal matrix elements and correlations that are built by the scattering. And so by the end of the day, you can actually infer what will be this entropy current. More details are in my paper. So just to get some feeling for that, let's analyze a more simple, it should be just one resonance here. you can actually write a simple formula for a situation where you have a single resonant static problem. And the entropy production, you can simplify the expressions I wrote in the previous slide for that in terms of these quantities. And by the end of the day, you have the entropy production in a static case, just basically the difference of these entropies in both reservoirs, and the actually thing that produces entropy is this relative entropy given by the standard way, in a standard way. So you can actually infer all that from the scattering matrix if you do everything correctly. So yeah, so in this sense we are able to reproduce the static case with our theory. Now let's see what happens if you consider quantum pumps or if you consider an external drive. So basically the idea is that you have your system and you have an external drive which makes the resonances go up and down. And by doing so, this will do some work, and actually there is some back action force that will eventually lead to some dissipation. And that's the idea. And to simplify even further, we are trying to understand what happens at zero bias. This is introduced just for the sake of simplicity, but one can do better than that. So the name of the game is the same as I presented before for the previous case of a single contact. We expand the S matrix in powers of the drive. Yeah, first zero order, first order, second order. The zero order is a static case. The first order is the reversible, and the second order is actually connected to dissipation, to reversible processes. And also concerning what comes out of the system, we also make the same kind of expansion, and collecting all the results together, we arrive at some looking formula for the entropy current and for the heat current. Now we have to go into the pain of doing all this Wigner transforms, Moyau expansion and stuff of this phi in and out. And by doing so, we identify the first order, the quasi-static limit, with a simple result. Well, actually, it's reversible, so there is no big surprise. And in second order, we have let's say something that looks like a reversible process plus this guy, and remind you that this phi out contains all the correlations, and therefore the entanglement produced by the scattering through the system. And working out what comes out next is that we can associate this term, this extra term, with the dissipated powers pumping by the drive, and this is basically a back action force, and this is the correct expression that one has to that. So in this sense, this is what comes out of the calculations. Now, to close all that, we need to understand what is actually, what can you actually measure. So in the internal region, which was characterized by the circle that I told you before, you have a coherent propagation, a unitary propagation, and the relaxation processes will only take place outside this region. So what happens inside, you have to compensate for what you measure outside, and this is what we call inside-outside duality. And so if you use that, by measuring what happens outside, you can infer what you can obtain from the inside of the drive. And then you can play all sorts of games. You can average the cycle. Since you don't have a bias, basically the current will go in and out. But by the end of the day, you know that there is some energy pumped by the drive, and this is released into heat, and we can show that. So I wish I could present you with something about fluctuations, but the calculations are unfortunately a little bit too, well, They took a longer time than I expected, but this is a line that we are looking at now. So this is all these results refer to average quantities, first moments, and now we are looking to fluctuations to understand the realm of quantumness here. So that's my conclusion. So there was not even the buzz. You have to turn it off. I saw it's 0 there. So the Landauer-Büttiker approach avoids this partition problem that that actually was spoiling all the other calculations, in our opinion. And it's a natural thing. It's a natural mechanism, natural approach to describe this kind of problems. And due to this inside-outside duality, we can recover expressions for the entropy production obtained by standard thermoelectrics. And we can actually extend that to processes which are driven. So that's basically it. Thank you.
Oh, thanks, Caio. Nice talk. Questions?
Yeah, I have a question. So you compute the here